Have you ever pondered what happens when a nuclear bomb detonates? The power held within nuclear bombs is nothing short of awe-inspiring. With a single detonation, cities can be reduced to ashes, and entire landscapes forever altered. Yet, despite their destructive capabilities, these devices are also a testament to human scientific achievement. From the splitting of the atom to the creation of the first nuclear bomb, our understanding of nuclear power has been a journey of discovery and innovation. These weapons, as terrifying as they are, represent a profound breakthrough in our understanding of the universe. The principles that govern their operation are the same that fuel the stars and power the sun. However, nuclear bombs are more than just a historical milestone or a scientific marvel. They are a stark reminder of the immense power that humanity now wields, a power that must be handled with the utmost caution and responsibility. Dive in with us today as we unravel the science behind a nuclear bomb. A nuclear bomb, at its core, is a sophisticated blend of physics and engineering. It's a marvel of human ingenuity, although one we hope never to see used again. But what makes this devastating weapon tick? What are its vital components? First, we have the fissile material. This is the heart of the bomb, the source of its immense power. Usually, this is either uranium or plutonium. These elements are chosen for their ability to undergo nuclear fission, a process where an atom's nucleus splits into smaller parts, releasing a tremendous amount of energy. Next, we have the tamper. This is a layer of material, often made from uranium or lead, which surrounds the fissile core. The tamper serves two critical roles. It helps to reflect neutrons back into the core, boosting the efficiency of the fission process, and it also acts as a barrier, containing the nuclear reaction long enough for it to fully develop. Third in our lineup is the conventional explosives. Now, you might be wondering, in a nuclear bomb, what's the role of conventional explosives? These are used to trigger the nuclear reaction. They compress the fissile material into a supercritical mass, a state where it can sustain a nuclear chain reaction. Finally, we have the neutron initiator. This is the spark plug of the nuclear bomb. It's a small device placed at the center of the fissile material that, when triggered, releases a burst of neutrons. These neutrons then collide with the atoms of the fissile material, causing them to split and release more neutrons, which then cause more atoms to split, and so on. This creates a chain reaction, a self-sustaining cycle of fission, and it's this chain reaction that unleashes the bomb's destructive power. These components, when combined, create a chain reaction of nuclear fission. It's a dance of particles and energy, an interplay of forces that, in a fraction of a second, can unleash a power greater than the world has ever seen. The heart of a nuclear bomb lies in the chain reaction it instigates. Now, this isn't your typical domino effect scenario. It's far more intricate and, dare we say, explosive. Let's imagine a dance floor, where our dancers are the atoms of a fissile material like uranium or plutonium. A neutron initiator, our DJ, releases the first neutron, our lead dancer, onto the floor. This neutron, with its energetic moves, collides with a uranium atom, splitting it in two. This dance-off releases energy and, importantly, more dancers, or in our case, more neutrons. These newly released neutrons then take to the dance floor themselves, each colliding with another uranium atom, splitting it apart and releasing even more energy and yet more neutrons. This is the essence of a chain reaction. One event sparks another, which sparks another, and so on. It's a party that, once started, doesn't stop until every atom has been split. So how does this translate to the workings of a nuclear bomb? Well, in the heart of the bomb, the neutron initiator releases the initial neutrons into the fissile material. These neutrons collide with the atoms of the material, splitting them apart and releasing more neutrons. This process repeats itself, with each split atom releasing yet more neutrons, which continue to split more atoms. This rapid and continuous chain reaction generates an immense amount of energy in a very short period of time. And it's this energy that results in the monumental explosion we associate with nuclear bombs. The splitting of a single atom might not yield much energy on its own, but when you have millions upon millions of atoms all splitting in a fraction of a second, the cumulative effect is staggering. This continuous chain reaction is what leads to the massive explosion we associate with nuclear bombs. It's a dance of atomic proportions, a destructive ballet choreographed by the laws of physics. And it's this chain reaction, this unending atomic tango, that forms the devastating heart of a nuclear bomb. The culmination of this chain reaction is an explosion of immense proportions. Now let's delve into the specifics of how this occurs. Imagine a ball of subatomic particles, all eager to break free, contained within a shell of conventional explosives. When detonated, these explosives compress the fissile material, the uranium or plutonium at the heart of the bomb, into a much smaller, denser mass. This compression is akin to a crowd of people being squeezed into a tiny room. As the room gets smaller, the people inside it bump into each other more frequently. Similarly, when the fissile material is compressed, the atoms within it collide with each other more often. This increased collision rate enhances the chain reaction we discussed in the previous scene. The increased density and enhanced chain reaction mean that a greater number of atoms are splitting and releasing energy at a faster rate than ever before. This energy, previously held in the bonds between the protons and neutrons in the nucleus of the atom, is now set free. The energy release is instantaneous and immense. It takes the form of a shock wave, a sudden change in pressure, temperature, and density, which moves outward from the epicenter of the explosion at incredible speeds. This shock wave is responsible for the destructive blast damage associated with nuclear explosions. Alongside the shock wave, a tremendous amount of heat is generated, reaching temperatures hotter than the surface of the sun. This heat causes fires and burns, adding to the destructive force of the explosion. Lastly, the explosion releases a flood of radiation, including gamma rays and neutrons. These high-energy particles can cause radiation sickness and are a major factor in the long-term health hazards of nuclear explosions. In essence, the explosion of a nuclear bomb is a rapid, violent release of energy, the result of a chain reaction that has been compressed and accelerated to an extreme degree. This rapid energy release is what we witness as the devastating explosion of a nuclear bomb. The aftermath of a nuclear explosion is just as fascinating as the explosion itself. It's a spectacle of raw, destructive power that leaves a lasting impact, with effects that can be felt for years, decades, even centuries to come. First, there's the shock wave. This is an intense wave of pressure that expands outwards from the explosion's epicenter. It's so powerful that it can crush buildings, shatter glass, and cause widespread devastation. This initial shock wave is followed by a wave of intense heat, hotter than the surface of the sun. This heat can ignite fires, cause severe burns, and lead to widespread destruction. But the physical destruction is only the beginning. The real danger of a nuclear explosion lies in the radiation it releases. This radiation consists of high-energy particles that can penetrate living tissue and cause serious, often fatal damage. In the immediate aftermath of a nuclear explosion, this radiation can cause acute radiation sickness, a severe illness characterized by nausea, vomiting, and a rapid decline in health. And then there's the radioactive fallout. This refers to the radioactive particles that are thrown into the air by the explosion, then fall back down to Earth. These particles can contaminate the environment, making it unsafe for humans and other living things. The effects of this fallout can be felt for years, even decades after the initial explosion, causing an increase in cancer rates and other health problems in affected populations. But a nuclear explosion doesn't just affect the physical environment, it also has profound societal impacts. The destruction and loss of life can lead to widespread trauma and societal disruption. Moreover, the long-term health effects and environmental contamination can lead to displacement and societal unrest. So, to summarize, a nuclear bomb works by initiating a chain reaction that releases a vast amount of energy in the form of an explosion. This explosion produces a shock wave and intense heat, causing widespread physical destruction. The explosion also releases radiation and radioactive fallout, which pose serious long-term health and environmental risks. In essence, a nuclear bomb is a device that harnesses the power of the atom to create a weapon of mass destruction. It's a testament to the power of science, but also a stark reminder of the potential for that power to be misused. As we've seen, the workings of a bomb involve complex physics and chemistry, and the effects of its explosion are profound and far-reaching. But despite the destruction it can cause, the science behind it is fascinating. It's a stark illustration of the power of the atom, and a sobering reminder of the responsibility that comes with wielding such power. Understanding the science behind nuclear bombs helps us appreciate the power they wield and the importance of using such power responsibly. If you've enjoyed this deep dive into the science and implications of nuclear bombs, don't forget to hit that subscribe button. Give us a thumbs up if you've learned something new today, and don't hesitate to share your thoughts and questions in the comments below. Your engagement helps us create more content that fits your interests. Until next time.